Friends, today we are going to discuss a very important topic related to pump, that is called its minimum recirculation flow. There is a terminology called minimum continuous stable flow, MCSF. What is MCSF? Now we know that when a pump is running at lower flow, there is a possible or some flow. If you run the pump with discharge valve closed condition, your discharge flow will be zero, but at pressure will be high. So what will happen? There will be a problem in your balancing, axial balancing of the pump, and there is a chance, there is a possibility of churning of the fluid inside the impeller and casing. Due to this churning, the heat will generate and your shaft may seize. So there are a lot of problem can take place. So you have to do, while running a pump, you have to first find out what is its minimum continuous stable flow. How you will calculate the minimum continuous stable flow? Now minimum continuous stable flow is that is by manufacturer experience. The pump which are manufactured in the manufacturing lab, when they are taking trial or taking test of the pump, they will reduce the flow gradually and see where the problem will take place. So when the problem take place at minimum flow, that they record the flow and they define this is your minimum recirculation flow. Below this flow you cannot run your pump. Normal thumbs rule is telling that if your rated capacity of the pump is Q, then you should not run your pump below 20% of the rated capacity. Then what actually happened? Because that lower flow, what is happening, your impeller diameter, I diameter is bigger than the flow going to inlet to suction I. There is a separation of flow. So what will happen at discharge? Some flow will recirculate through the veins, through the cavity of the veins and your shrouds to the suction again. So this will create problems, abnormal sound, etc. Radial thrust also increase, because I have already told you discharge pressure will high, so our axial unbalancing will be there, thrust bearing load will increase, that's why the thrust bearing will make damage. Cavitation, yes, certainly cavitation erosion intensity will certainly increase. Your pressure rise will take place, that means your stopping box pressure will also gradually take place, that means your mechanical seal is going to fail. Then power requirement will also increase. So all this combination you have to do the test and finally recommend what will be your minimum recirculation flow. This is the picture. You can see from the pump is taking suction from the suction tank, and giving discharge to the process, and some flow through orifice. It is going to, there is a control orifice, it is going to the suction. So this if our process requirement is reduced, then then some flow reduced or increased, then this flow will close, and when the process requirement will reduce, then this valve will open, and for pump, so throughput will increase certainly, but it will increase by how? By increasing the flow, by passing the some flow of discharge flow to the suction again. So pumps should not run dry, because I have told you, due to high pressure, your axial thrust will be unbalanced, your stopping box pressure will increase, mechanical seal failure can take place, there will be churning, so your there is a seizing of shaft will take place between shaft and impeller. So lot of problems may arrive. So your aim should be to not run the pump dry or dry condition. This is the ARC valve. I have told you that this is the ARC, which is the disc valve, main disc. This is just inlet side of the ARC valve. This is the discharge side of the ARC valve. This is mounted on the discharge nozzle of the pump, and this is mounted with the discharge process side pipes. When the pump running with full load, this is the automatic recirculation line. When the this disc is operating against the spring force here, normal condition. When pump is not running due to the spring force, the disc will tightly fit on the seat. When the pump is running due to the high pressure, this will overcome the spring force, the valve will open and the flow will take place from this. When the flow is not there due to spring force, it will come down, and then this valve will open and some flow, recirculation flow will take place. These are the three conditions of the recirculation line. You see, when the pump is running at full flow, then what is happen? Full flow due to high pressure, this disc will come up, and this stem will close the port holes of the recirculation line, close, and then full flow will from the disc will to the process line will take place. When flow has come down due to the pressure, discharge pressure has come down, then due to the spring force it will come slightly down. This will allow minimum flow. This will allow some flow to the process, and this port will open. Some port will open, and then from this port some fluid also pass to the recirculation line to the pump suction again. And when you close the valve, discharge valve, there is no pressure on the downstream of the valve. So due to spring force, it will completely close, but pump is running. So this port will open, and from this port, recirculation line will open, and it will go to the pump suction. These are the three conditions may exist in the recirculation ARC valve. This is the four-way we are controlling the capacity or capacity of a pump. You can throttle it. Once you discharge a pump, this is the pump, this is suction line, there is discharge line, there is a discharge valve. You can throttle it, so you can reduce the flow. Then you can bypass it. Some flow, the discharge valve will full open or some slightly closed condition. You can open the bypass valve. That also a way you can control. You can on off the control. Your pump is running. Your requirement is not there, so you can close the valve by this motor switch on and off. And this is the variable speed, that is also an instrument. With this you can increase and decrease the RPM of the motor like this, and with this we can control the discharge of the pump. The four-way we can running the pump. The four-way you can see that is the H versus Q curve, and the normal running. This is your suppose this is your rated flow, that is equal to 10, and this is your rated pressure, that is equal to 10. So what is the power requirement? 10 into 10, that is equal to 100. But when you are throttling means you are closing the discharge valve, the system resistance the downstream pressure will increase. When downstream pressure will increase, the new system resistance curve will cut the performance curve here. So you see your new flow has come down from 10 to 7, but your pressure has increased from 10 to 12.7. So what will be your now new condition? What is your power requirement? Now 12.7 is your new pressure, 7 is your new flow, that is 89. Similarly, for bypassing, what will happen? This is your running condition at rated flow 10 into 10. When you are bypassing some fluid means your flow has increased. When bypass valve is open, so flow has increased. When the flow increase, the system resistance curve will be more flat, and it will cut the H versus Q curve here. You can see the flow increase from 10 to 12.4, and your pressure has come down to 10 to 6.6. So what will happen? Your new power requirement will be 12.4, your new flow, and pressure is 6.6, that is 82. On-off control means suppose you need not require to run the pump 70%. You need suppose you're in a tank, you are discharging flow. Tank has two levels. So once the full level has taken place, we have to stop the pump. And suppose you are running 70% of your pump to keep the level, to maintain the level. So what will be your power at full load, and what will be your power requirement? Now 100 is your rated power, and 70% time you are running the pump. So 70.7 into 100, and 30% time you are not running the pumps. Then at that time power requirement is 0, because flow is 0, flow into head, flow is 0, so power requirement at 30% time is 0, and at or 70% time it will be 70.7 into 7% time it is running with 100, so this will be 70. And VSD means variable speed drive. You are controlling the RPM of the motor. So this is your normal running condition, 10 into 10, 10 flow, 10 pressure. So when you are reducing the RPM, your performance curve will come down from this point to this point, and your system resistance curve will cut the new performance curve here. So here you can see the flow has come down from 10 to 7, and pressure has come down from 10 to how much? It is 6.4. 6.4. New pressure is 6.4. So your new power requirement will be 7 into 6.4, that is 45. So all these pictures, previous slides, we are calculating here mathematically. That also you can see the initial condition 10 into 10, 100. Now for the throttling case, it is Q has come down to 7, head has increased to 12.7, so new power requirement will be 89. Similarly, bypassing, the flow has increased from 12.4, pressure has come down to 6.6, new requirement will be 82, you see 82 here. On-off condition it is 70, and VSD it is power, and VSD power has your flow has come down, discharge pressure has come down, so power requirement will be 45. So if you see with this, you will see with this, there is another one slides are there, I think so. If you another one slides are there, another one slides are there, that is called these slides. You see here you can see the this line is VSD line, this is your on-off control, this is your on-off control, this is your throttling control, and this is your bypass control. Your bypassing control will take throttling, this is your bypassing control, this is your throttling control, this is your on-off control, and this is your VSD. So VSD it always take less power, then your on-off control 70% time you are running, and back rest time or you are taking not running the pump, and then your bypassing system. Bypassing system means your pressure quantity has increased, flow has increased but reduced flow, that is the third control, and this is the fourth where maximum power will take place, that is called the throttling. This is the throttling, this is called the throttling graph. So this picture is clear. From here you come to know the VSD are the way we can, economical way by which we can control the flow of a pump. I think I have tell you everything in the slides. If you go through these slides, your all concept regarding flow control, ERC valve construction, your picture will be clear. So if you have still doubt you can ask me in my mobile number, in my mail ID. I will certainly reply you, or certainly or talk to you. But there is a question you may be asked: what are the process of control pump flow? That is the four process. Which process is more economical? Then you can say that VSD, variable speed drive, is the most economical process, and you can prove it also mathematically. Thank you very much.